In this section, we will explore inverse trigonometric functions. Let's start with an example. The population of a city has risen and fallen over a 20-year interval. Its population may be modeled by the following function. Y equals 12,000 plus 8,000 times the sine of the quantity 0.628x, where the domain is in the years since 1980 and the range is the population of the city. Based on this model, what is the predicted population in 2010? So we are being asked to determine what is the predicted population. So the first thing we have to do is determine whether or not we are being asked to solve for the domain or the range. So the domain represents years, doesn't it? And the range represents population. So we are being asked to solve for the range. The range would be the output or the y value. So I know that I need to solve for y. And so I'm going to use that equation. And I am going to substitute in the x value that I hope has been given to us. The x value would be the input, and the input is the domain. Now the domain has been listed for us as years since 1980. So we are talking about the year 2010. So if the domain is the years since 1980, how many years have passed between 1980 and 2010? So let me just write this out. I'm going to say that the year 2010 is 30 years, right? 30 years after 1980. Okay, so I'm not going to use an input for x of 2010. I'm going to use an x value of whatever 2010 minus that 1980 start point was. So I'm going to use an x value of 30. Okay, so this represents 30 years after the 1980. So I'm going to put 30 in. And so this problem becomes just putting this all into my calculator. I'm going to literally just grab a calculator and type in 12,000 plus 8,000 times the sine of the quantity 0.628 times 30. Now I want to make sure I'm in radian mode because I do not see any degree symbols on this. So when I put that into my calculator, I got y equals 11,923.55379. Now remember, that output represents a population. So this is a population in 2010. Now, I don't think it makes sense to have a partial population. So I'm going to make a decision to round to the nearest whole person, and I'm going to say that in the year 2010, the population of the city is approximately, let's call this 11,920. Now sometimes they tell you to round down. There's arguments to say round down because you're not going to have half of a person, but I'm going to go ahead and just round up, and because this is all estimating anyway. 11,920. I'll say 3, but you could also say 924, couldn't you? And it's going to be that many people. Okay. But what if we wanted to do the reverse? What if in that same word problem we wanted to predict the year in which a city has a certain population? So in this same example that we just looked at, now we are being asked, in what year will the population reach 18,000? So the population of 18,000 has been given, and remember, the range is the population. So we can say that our y value has been given to us as 18,000. So I'm going to go ahead and substitute that back into the original equation that was given to us and solve for x. So I'm going to have 18,000 equals 12,000 plus 8,000 times the sine of 0.628x. To solve for x, I first need to work on isolating this piece, right? That piece is connected by addition to the 12,000. So I'm going to subtract that 12,000 from each side. So 18,000 minus 12,000, and then on the right hand side, I'll just go ahead and write this out so that you can see what is actually happening here. And on the left hand side, 18,000 minus 12,000 is 6,000. And on the right hand side, the 12,000s cancel, and I'm left with 8,000 times the sine of 0.628x. All right, so I said times, 8,000 times. So I'm going to get rid of that 8,000 by doing the opposite of multiplication, which is division. And 6,000 divided by 8,000, the zeros, right, the thousands are going to divide out. So I'm going to get 6 over 8, which is 3 over 4, and I'll call that 0.75. And that's going to equal, the 8,000s reduced to 1, so that's going to equal the sine of 0.628 times x. But now we're in a quandary. How do we isolate this x? How do we get that x by itself? We haven't learned how to, I guess you'd say, get that x out of the argument of the sine function. So to solve this equation algebraically, what we need is a process that will isolate the argument of the function. And this process is what undoes the original trigonometric function. And that is called finding the inverse of a function. So we're going to spend the rest of this time talking about how we find an inverse of a function. And then we will come back later to this problem and go ahead and solve it. Before we can talk about inverse trigonometric functions, let's just remind ourselves of what it means to find an inverse function. So we'll start out with, let's say, the equation of a line, y equals 2x plus 3. Do you remember how to find the inverse of this equation? You may have learned that to find the inverse, you reverse the inputs and the outputs. So instead of y equals 2x plus 3, we would have x equals 2y plus 3. And then to actually solve that equation so that you have the inverse function, you would solve the equation for y. So if I subtract 3 on both sides and divide by 2, I get that x minus 3 over 2 is equal to y. So we would say that in the original equation, y equals 2x plus 3, that the inverse of that is y equals x minus 3 over 2. And these are functions because if I put an input in, I will only get one output. Okay, so that is the definition of a function that we have to be careful about. Let's look at one more that sometimes can be a little tricky. So if we have, let me take a look at the equation y equals x to the second power, and we do the same process. So the inverse is going to be, so now I'm going to write x equals y squared. Now let's think about, first of all, y equals x squared. Y equals x squared is the graph of a parabola, right? Opening up and opening up. You may remember something about horizontal line tests or vertical line tests. A vertical line test, if I run a vertical line through this function, because it only goes through one location, that's what tells me that this is a function. I can look at this same picture and do a horizontal line test on it, And that horizontal line test, because it's going through in two places, that's what tells me that the inverse of this function is actually not a function unless I do something. And that something is that I'm going to limit the possible outputs. And I'm going to limit the possible outputs to only positive values. So if we have y equals x squared, we would say that the inverse is, I would have to square root both sides, and I would get y equals, normally you would get plus or minus, but we're going to just use the plus version of this to ensure that not only is the original function a function, but so are the possible outputs. So are the possible outputs. If I don't put that limitation, then I will not have an inverse that is a function. And the reason I'm making such a big deal out of that is because we're going to have to worry about that when it comes to trigonometric functions. And we'll take a look at that here in just 1 second. So for trigonometric functions, the domain or the input always is the measure of the angle, right? We're going to have like the sine of theta or the cosine of theta, theta being that angle input. The range is the output. The range is the output. What pops out when we do that? You know, the sine of, say, 30 degrees. We know at 30 degrees that our sine is going to be 1/2. So the 1/2 is the output. For the inverse, it just swaps, right? So now the domain is that ratio that was the output, and the range for the inverse is the angle, which was an input. All right. Now I want you to be careful here about notation. If f of x is equal to the sine of x, then we say that the inverse sine function is written as f with this little -1 above it. That little -1 means inverse, so we are going to say f inverse of x equals sine inverse of x, or sometimes instead of writing sine inverse of x, you see the notation arcsine. They mean the same thing. And the caution is that that -1 that's up in f inverse or sine inverse does not mean 1 over the sine of x. The -1 in this case means inverse, so be careful about that. Let's look at an example. Part A. If the sine of some input, in this case it's the angle, pi over 6, is equal to some output, which we know the sine of pi over 6 is equal to the output 1/2, then the inverse sine is going to reverse the inputs and the outputs. So what was an output of 1/2 now becomes the input of inverse sine, and what was an input, which was pi over 6, now becomes the output. And let's take a look at a unit circle to make sure that we agree with that. Over in the first quadrant, we see the angle pi over 6, and we see that output of 1/2. But the question is, why do we only include pi over 6 and we don't also include 5 pi over 6? Because if you take a look over in the second quadrant, you see that 1/2 is also an output when the angle is 5 pi over 6. So why not put 5 pi over 6 here as well? Well, the answer is because if we're going to actually call this inverse sine a function, then the definition of a function is that that input of 1/2 can only have one output. So should the output be pi over 6 or should the output be 5 pi over 6? Well, it could really go either way, but it can only be one of them for sure. And there's a historical choice here that is used in all of mathematics, and not only that, but in your calculators. For y equals inverse sine of x, we say that it has a domain of -1 to 1, including both of those values, and it has a range of -pi over 2 to pi over 2. We have brackets on that to say that it includes both of those values. Now, where is that space between negative pi over 2 and pi over 2? Well, pi over 2 is up at the top, the positive y-axis, so that includes all of the first quadrant. And then negative pi over 2 is in the same location as 3 pi over 2, so that includes all of the fourth quadrant. That will allow us to take care of positive values and negative values. Could there be a range other than negative pi over 2 to positive pi over 2 that would also include both the positive and the negative outputs? Absolutely. But at some point in history, a decision had to be made. And the decision that was made is this decision that I've given you. So it's always going to be in your calculator and in math books, only the outputs between negative pi over 2 and positive pi over 2. So going back up to the top, this 5 pi over 6, you'll notice that 5 pi over 6 is not in that space. And so your calculator would never tell you that that is an output. Part B. Now let's take a look at a cosine function. If the cosine of pi is equal to -1, then we know the inverse cosine of -1 should equal pi. We're just going to reverse inputs and outputs. Let's take a look at the unit circle, and sure enough, we see over here at pi that there is a cosine output of -1. But the question again is, why are we limiting it to pi? Couldn't we say negative pi? So here is pi. Couldn't we say negative pi as well? Well, like we talked about with the sine function, in order for the cosine inverse to be a function, there can only be one output. And so there's a historical choice made here as well. The inverse cosine function has a domain of -1 to 1, and it has a range of from 0 to pi. And both of these have brackets on it, meaning that it includes both of those values. So notice that if we start at 0 radians and then go to pi radians, that's taking care of the first quadrant, and that's also taking care of the second quadrant. And that is where the positive and the negative cosine values exist. And that is what calculators use as well. And so this dashed line where I showed, even though that might be a possible output, it's not the output that we're going to use in order to make sure that that inverse cosine is a function. And one more example. Part C. If the tangent of pi over 4 is equal to 1, which I think is true, then inverse tangent of 1 should equal pi over 4. Now, let's see, does the unit circle help us? Well, let's just go back to the original function. Is the tangent of pi over 4 equal to 1? Do we agree with that? I do agree with that, because at pi over 4, remember, tangent is sine over cosine. So in this case, the sine of pi over 4 is the same as the cosine of pi over 4. So when we divide those, that's what creates the 1. But you'll notice my question here, why can't we also use 5 pi over 4? If you go down into the third quadrant for 5 pi over 4, you would have the same idea. It would be a negative over a negative, same values. Why doesn't that also work? The answer is that historical choice again. The inverse tangent function, y equals inverse tangent of x, it has a domain of all real numbers, and it has a range from negative pi over 2 to positive pi over 2. That's the same that we saw for the sine function. However, in this example, notice that there are parentheses, not brackets. And that's because we saw in earlier sections that at pi over 2 and negative pi over 2 for the tangent function, we have undefined outputs. That's where we see the vertical asymptotes. So we can't include those values. This is a historical choice. It allows us to see both positive and negative tangent inverse outputs, and it is what calculators use. And we'll go to the calculator in just a minute so that you can actually see that. All right, let's now summarize everything that we just said. The inverse sine function, y equals inverse sine of x, has a domain of -1 to 1, including both those values, and it has a range of -π/2 to +π/2, including both those values. Now, in this image, I have put not only the original function, the original sine function, but I've also included in red the inverse sine function. Now, I just want to point something out here real quick. If you go and look at the sine function, right, it's that wave that we've seen before. You know, that sine function does pass a vertical line test, doesn't it? If I could draw any vertical line, it would only go through one location. It does not, however, pass the horizontal line test, does it? And because of that, that's what tells us that unless we do some limitations, we are not going to have an inverse sine function. So that's why, again, that's why we had to do a limitation. And that limitation is the value or the function that you see graphed in red. All right, and if you also remember something about inverse functions, you'll remember that inverse functions are symmetric about the line y equals x. So you see that diagonal line y equals x, and if you just focus on, let me just get rid of some of this drawing on here. If you just focus on the part that is in black for the sine function, and then you focus on the part that's in red for the inverse sine function, you will see that they are symmetric about that diagonal line y equals x. So those are the only values that we're interested in. For the cosine function, you'll see in this graph in black, now we have the cosine function graphed, and the inverse cosine has a domain of -1 to 1, has a domain of -1 to +1, and it has a range from 0 to pi, including both of those values. And again, we see that symmetry over the line y equals x. For the tangent function, in black we see the tangent function, and inverse tangent of x has a domain of all real numbers, and it has a range only for those outputs of -π/2 to pi/2, not including -π/2 and +π/2 because of the vertical asymptotes. Notice that the ranges of the inverse trigonometric functions are given in radians. Equivalent degrees would work as well. So for the sine function, instead of -π/2, I could say -90 degrees to +90 degrees, including those values. For the cosine inverse, I could say 0 to 180 degrees, including both of those values. And for the inverse tangent, I could say -90 degrees to +90 degrees, not including those because of that vertical asymptote. So let's take a look at some examples. Part A, evaluate in radians inverse sine of the square root of 3/2. All right, so I'm going to write sine inverse or inverse sine, however you want to say it, of the square root of 3/2. What does that equal? Well, let me just remind you that the output, this output, right, is going to be an angle. So the question that we're asking ourselves is, what angle produces a sine of the square root of 3/2? And that angle has to be between +π/2 and -π/2. It can only be in quadrant 1 or 4. And because it's a positive square root of 3/2, we know that that answer, that angle measure, is going to be in the first quadrant. So in radians, we would say that this answer is only π/3. Okay, part B. Now let's evaluate in degrees. inverse sine of negative square root of 2 over 2. So we are again looking for what angle would have an output of negative square root of 2 over 2. And we're in that same, I'm just going to draw a line here, sort of call it like a border, right? We can't cross over that border. Now there's no angle that's going to produce a negative sign in quadrant 1. So that means we are in quadrant 4. And we see negative square root of 2 over 2, it looks like down here at 315 degrees or 7 pi over 4. But if we use that positive, say 315 degrees, in order to get to 315 degrees, we would have to cross over that border. So we're not going to write 315 degrees. We're actually going to write something that doesn't make us cross over the border. We're going to say negative 45 degrees, and that is what your calculator would say as well. All right, now let me just erase some of this, clean this up a little bit. Let's take a look at part C, which says inverse cosine of negative square root of 3 over 2. All right, so let's remember, let me write this down. Cosine inverse of negative square root of 3 over 2. We are looking for the angle. And that angle has to be between 0 and pi, right? And let me just go up to part A and B. For those, it had to be between negative pi over 2 and positive pi over 2. Right, that was the same thing here. So we had to limit ourselves. Actually, let me not draw that arrow down because the part B was in degrees. So let me say that one would be from negative 90 degrees to positive 90 degrees. But in radians cosine inverse, we would see, let's see, what angle produces negative square root of 3 over 2? It looks like it's going to be right here. And so that's going to be an angle measure of 5 pi over 6, right? Because we are only interested in the angles between 0 and pi. So even though even though 7 pi over 6 would also produce a negative square root of 3 over 2, it would make us cross over that imaginary border. So that would not be the output that we're looking for. And then the last one is for tangent. Tangent inverse of negative 1 is going to equal, and we're looking for the angle measure that is in the space between negative pi over 2 and positive pi over 2. And so to have a negative 1 output, that's going to be where your sine and cosine are the same values, but the opposite. And so that occurs down in the fourth quadrant at 7 pi over 4 or 315 degrees. And I'm going to call that negative 45 degrees to make sure that I don't cross over that border.